Hello everyone, my name is Soham Bhattacharya. I'm from the Department of Electrical and Computer Engineering at Rowan University, which is in United States of America. My project is implementation of a hardware accelerator with floating point unit based Euler and modified Euler solver for an ordinary differential equation. I, along with my advisor, Dr. Chakraborty, had started this project in the year of 2022, where we were in search for different types of models for hardware accelerators, which will do some kind of specific task. This project is specifically for my thesis towards PhD dissertation. Regarding the presentation overview, I will cover some of the possible areas starting from introduction to future work, depending on the roles of those topics. In the introduction, I will discuss regarding the ordinary differential equations and why it is called as the nature's language, as well as the usefulness of hardware accelerator. We will also discuss the goal of this study in the introduction. After that, I will move towards the problems which had been faced previously regarding single core and multi-core architectural models and how we can overcome these limitations. I'll describe about a short literature review on this presentation, followed by the architecture description of my hardware accelerator for solving an ordinary differential equations using two of the numerical methods, which are Euler and modified Euler method. Along with that, I will discuss about the implementation of the hardware using two custom instructions. The last part will be the experimental results and how I gained the results regarding the hardware along with the conclusion and future work. So let's start. In this era of high performance computing, hardware accelerators play a crucial role handling a specific task while offering some of the significant performance improvements as well as diminishing the power requirements or the power consumption. Ordinary differential equations, also known as the nature's language, play a fundamental role in modeling as well as simulating various dynamical systems. They can provide an exact and analytical way to find exact solutions, whereas there are different types of problems regarding these ordinary differential equations, which I will discuss in the next slides. The goal of this study is the implementation of a hardware accelerator for the Euler as well as the modified Euler methods of numerical analysis in solving ordinary differential equations. This work has been done in Xilinx VIVADO design suite. Also, the VHDL hardware description language has been used for implementing the hardware accelerator. There were a lot of problems while implementing any kind of single core architecture behavior model for doing any kind of specific task in the previous years. So we will discuss about the problem and the solution for those in the next slide. Around 15 years ago, there were some kind of setbacks on the path of linear scaling due to the complexities of power dissipation, leakage current, as well as wear delays. Stagnation arose at that time in the improvement of single-core microarchitecture. So hardware manufacturers failed to improve single-core microarchitecture and thereby shifted their attention towards some new design models. At that time, multi-core microarchitectural design comes into play. So what's this multi-core? Multi-core is nothing but incorporation of multiple cores on a single die, though those approach were short-lived and provided some kind of insufficient approaches in diminishing power of the computing as well as increasing performance of the device. For that reason, hardware manufacturers move towards some kind of domain-specific architectures to provide some kind of specific task solution. These approaches were known as the domain-specific architectural approach and has been successfully implemented in the graphics processing unit. Regarding the ordinary differential equations, as I had discussed as the natural language, there are some of the complexities in solving those equations due to the complex nature, or you can say like complex behavior of those equations. And for that reason, we use some of the numerical methods to solve those equations, also to get some kind of approximate solutions from those equations. So we have developed two hardware accelerators for those two numerical methods, such as Euler and modified Euler numerical method. In my paper, I had discussed more literature review, but for this presentation, we will discuss a little bit of literature review for developing hardware accelerator for doing any kind of special task. So one scientist named F. Pardo first developed effective computational solution of the heat transfer processes that occur in soil and at the soil-air interface. The authors at that paper used HAND-LC and VHDL to project a 3D finite difference thermal model of the soil and had deployed that architecture onto an FPGA platform. After that, another scientist named A. Ibrahimi had developed different computational fluid dynamics problems such as Laplace and 1D Euler equations and stated that it can be implemented on Zynq 7020 FPGA evaluation device. I. Stimulus has implemented a hardware accelerator for single and double precision floating points and also offered in his paper that design investigation in terms of performance and hardware resources. According to the authors, the proposed method can reach up to 14 times more speed of a single CPU approach. More literature review had been discussed in my paper. So regarding the architecture description of my hardware accelerator, we will move forward towards the next slides. So at first, while developing or implementing the hardware accelerator, we have taken a specific ordinary differential equations, which will be implemented as a hardware accelerator using Euler and modified Euler method. The ordinary differential equations which has been taken for our paper is f is equal to xy cross x minus y divided by 2. After that, the microarchitecture of the implemented hardware accelerator comprises of Euler module or the modified Euler module, which has several sub-modules, along with a raster file, a 64-bit memory unit, as well as a control unit. According to the behavior of the numerical method, we had set some initial set of values for x0 and y0 as 2 and 1 respectively. This hardware accelerator will work using two custom instructions given to the test bench of the behavioral top module of the VHDL programming language. We have used some third-party Xilinx single precision or 32-bit floating point IP support to develop the accelerator for solving the differential equations using those two methods. Regarding the hardware implementation, Euler method module consists of a functional computational block which is termed as FCB, which will work according to the function taken in our architecture. And we had used two other IPs, which are addition floating point unit as well as a MAC unit. This MAC unit is nothing but a multiply accumulator unit, which states like it can do any kind of operation related to addition and multiplication. The next one is the modified Euler method module, which consists of a functional computational block, which is also the FCB, and it is same as the Euler method module. Along with that, we have developed another big functional block, which is BIGS FCN, which will do other operations regarding the behavior of the numerical method for modified Euler method. We have used two other IPs just like the Euler method module, which are addition floating point unit as well as a MAC unit. two custom instructions used for both the method based on the 32-bit RISC-V instruction format, which are Euler or modified Euler initialization instruction format, as well as Euler or modified Euler update instruction format. This update instruction format has two different modes, which are the flash mode as well as the store mode. Regarding the custom instruction, this Euler initialization as well as the modified Euler initialization 32-bit RISC-V based instruction format will be able to load all the values for x0, y0, as well as the step size h from the register files to the 64-bit memory contents. For the update instruction format, when the write enable is 1, the accelerator will operate for the instruction initialization as well as the update store mode. When the write enable is 0, the accelerator will operate for update flash mode for both the methods. If you see the microarchitecture design for the numerical ODE solvers, you can see there is a register file over here. It has a clock signal as well as a source register and a write enable. So this register file will be able to load all the values of the specific inputs like x0, y0 and step size h, and it will go towards the memory unit as content. This content will then be provided to the Euler as well as the modified Euler method module to deliver the results for the next iteration, which is termed as the xn plus 1 and yn plus 1. x0 and y0 is termed as xn and yn over here. So these values will again be stored to the memory unit in the specific addresses. The control unit will control all the other modules using the control signals. So in summary, if we can say, like, if we are giving any kind of custom instructions to the top module, it will deliver some of the approximate results of the iteration from xn plus 1 and yn plus 1 over the architecture. Regarding the experimental results for our hardware accelerated design, we have divided into three parts of our results, which are on-chip power consumption analysis, FPGA hardware resource utilization summary, as well as the timing summary. For the on-chip power analysis, we have used the Xilinx VIVADO power analyzer tool. This on-chip power has been calculated after deploying our hardware accelerator on Zynq ZC702 FPGA evaluation board. This accelerator will work at a clock frequency of 2.85 megahertz. If we see this slide, we can see that the Euler method hardware accelerator has a power consumption of 0.191 watt, from which dynamic sources has a 1% of the power usage, as well as the static sources has 99% of the power usage. In case of the modified Euler method hardware accelerator, the power consumption is 0.192 watt, on which dynamic sources has 2% of the power usage, as well as the static sources has 98% of the power usage. Let's start hardware resource utilization summary, in which we have used Zynq 702 FPGA board, through which we gained some of the results of the area consumed by our hardware accelerator in case of Euler as well as the modified Euler method. So for the Euler method, buffer gate, input output, and also the flip-flop is same for both the Euler as well as the modified Euler method. The only difference is the LUT used in the Euler method is 9% of the total architectural area, and also for the modified Euler method it is 13%, according to the behavior of the numerical methods. Also, the DSP for Euler method is 5%, as well as for the modified Euler is 10%. In case of the timing summary, Euler method has a total setup time delay of 6.832 nanosecond, whereas modified Euler method has a total setup time delay of 336.740 nanosecond. This whole difference is because we have make our design as a combinational circuit and we have used latency is equal to 0 for clock frequency of 2.85 megahertz. We can set that latency to any other number for making our Euler as well as the modified Euler method module as a sequential architectural model. The next total hold time delay for Euler method is 2.705 nanosecond, as well as for modified Euler method is 2.230 nanosecond. We have also determined the worst negative slack for both the methods as well as the word hold slack for the two numerical methods, which are Euler method as well as the modified Euler method, for a clock frequency of 2.85 megahertz. To conclude, we can say like two hardware accelerators for the Euler and modified Euler numerical algorithms have been constructed in our paper. We have used Xilinx VIVADO Environment as well as VHDL language for all of the work. So according to the experimental results, it has been seen that the Xilinx VIVADO single precision or 32-bit floating point IP support improves the performance of the hardware accelerator significantly. Also, we have analyzed some of the on-chip power estimation, FPGA hardware resource utilization, and timing summary in the article. This hardware accelerator will work effectively with the Zynq ZC702 FPGA evaluation board, and at this moment, this article will play a vital role in improving the ability of the findings to run on other FPGA boards like RDX7, Zynq, other models. Regarding the future work, we will use Xilinx floating-point IP core latency requirements, which will be more than 0, and making the system sequential to get better precision for our approximation results. The next research area which we will focus on will be pipelining the whole system to get better performance. Another area and also another vital area for our research will be incorporating it with a general purpose RISC-V code to see the better performance between them in terms of performance power as well as timing summary. We have used some of the references from our paper in this presentation. So this slide covers all the references which have been used for our presentation. Thank you so much for listening. Let me know the comments about this presentation. Have a good day.